This is chapter 7, part 2, and we're going to move on in the frequency domain by discussing the periodogram, which is how we estimate the spectral density. So this chi-squared property that we had in equation 13 motivates this thing called the periodogram, which is usually called IN and is the sum of the squared frequency components at the nth Fourier frequency, which can also be represented as the absolute squared value of the nth term of the discrete Fourier transform. And recall here that if you have a complex number z, the absolute value of z squared is z times its complex conjugate, or else if you just put z in the complex plane, then the absolute value of z is just this distance here. Okay, so log IN is an estimator of the log spectral density that comes from 14, and as we discussed in part 1, this equation 14 says we have asymptotically independent, identically distributed errors at each Fourier frequency, and that means we can use a signal plus white noise model for estimating the log spectral density using the log periodogram. One thing that needs a little bit of care is the periodogram is an inconsistent estimator of the spectrum. We see that the errors at each frequency in equation 14 don't become small as the length of the data n tends to infinity. So what happens instead is that the Fourier frequencies become closer and closer together, so it becomes increasingly reasonable to borrow strength between nearby frequencies. And so you can build up an increasingly accurate idea of the spectral density at a given frequency, but not because that frequency component is consistent, but because we get an increasing number of approximately independent estimates of that spectral density nearby in the frequency domain. Now, the spectral density is sometimes called the power spectrum and sometimes just the spectrum for short. It sometimes is convenient to think of physical analogies. So if you have the power of a wave, that's proportional to the square of its amplitude. That's kind of a physics thing. And the spectral density gives the mean square amplitude of the components at each frequency, and therefore the expected power. And therefore, from that physical analogy, the spectral density function is called the power spectrum. I think thinking of sound waves is a good thing for time series analysis, because that gives us this nice example of a time series where we very naturally think of frequency components, and thinking of the power at different audio ranges is a natural thing to think about. Okay, so the spectrum is the Fourier transform of the autocovariance function, and we should at least get a little bit of work out for our math muscles of computing this. So let's do that for the AR1 model, simple model, which I'm going to write in its more general form as phi of byn is epsilon n, where epsilon n is white noise with variance sigma squared, which I'm going to write as wn sigma squared, and phi of b is 1 minus phi 1b. And so let's go ahead and practice our algebra. I'm going to work in angular velocity rather than frequency, so it just makes the algebra a little simpler. So I'm going to set nu is 2 pi omega. And then if I want to work out lambda of omega, I know that what I need to do is work out the Fourier transform e to the minus I nu n gamma n. That's the Fourier transform represented in angular velocity rather than frequency. And then I can write out what this is because we know the autocovariance function of the AR1 model. This is the sum from n is minus infinity to infinity, e to the minus I mu n, phi 1 to the absolute value of n, sigma squared over 1 minus phi 1 squared. Okay, so how am I going to do that using using the geometric sum formula? Well, I'm going to take sigma squared over 1 minus phi 1 squared out. And then this is a kind of two-sided exponential sum. If it's one-sided, I could use the geometric sum series. So I'm going to write it. This is the thing I know how to sum. Phi 1 to the n e to the minus I nu n. And then I also have the terms from when n is negative. Again, I'm going to start from n is 0 to infinity. When n is negative, here I'm flipping the sign of n to be positive, so that I still have phi 1 to the n. N is negative, so e to the minus I omega n is being summed from over the positive range. So this becomes e to the I nu n. And then I've double counted the term from frequency 0, so I have to subtract that off again. So sigma squared over 1 minus phi 1 squared. This is a geometric series, so it's 1 over 1 minus phi 1 e to the minus I nu. And this is the same thing with a plus I nu. And then I have a minus 1. And now I just need to do some algebra. Sigma squared over 1 minus phi 1 squared. What do? I take 1 minus phi 1 e to the minus I nu. 1 minus, there should be a 1 here, phi 1 e to the I nu. And then I have on top a 1 minus phi 1 e to the I nu. And I have a 1 plus phi 1 e to the minus I nu from this term. And then I have the minus 1, for which I need to multiply these two things out. And that gives me 1. I get a minus phi 1 e to the minus I nu, a minus phi 1 e to the plus I nu. And then if I multiply phi 1 e to the minus I nu times phi 1 e to the plus I nu, then the I nu's cancel out and I get phi 1 squared. Okay, and then I can write this as sigma squared over 1 minus phi 1 squared. All the some terms cancel here. The e to the I news and e to the minus I news on the numerator cancel. And so I get 1 plus 1 minus 1, which is 1 minus phi1 squared. And then this thing on the bottom, 1 minus phi1 e to the minus I nu, 1 minus phi1 e to the plus I nu, I can write this as the absolute value of 1 minus phi1 e to the I nu squared. And then the 1 minus phi1 squareds cancel, and so I get sigma squared on the numerator. I can notice 1 minus phi1 e to the I nu is formally just the AR1 polynomial of e to the I nu squared, which by putting nu is 2 pi omega gives me what I have in equation 16. And then if I write this out in terms of sines and cosines, then I think I'm not going to go through the algebra right now just to check that that is indeed equal to 1 plus phi squared minus 2 phi cos 2 pi omega. So there you go. We've done our algebra. The thing that you can't see, well, the nice thing about this, the form, the reason I've written it like this is because it does in fact generalize, and I'm not going to go through the full argument for that. I'm just going to write out the result, which is that if we have a general armor PQ model, phi of byn is psi of b epsilon n, then the spectrum has this form. You have the phi of e to the 2 pi omega, 2 pi I omega on the top, the psi of e to the 2 pi I omega on the bottom, take the absolute value squared, and that's called a rational spectrum. It's computationally convenient, and mathematically, if we want to, we can, it helps us analyze it. One thing you can see from 17, you can start seeing when you're going to have large amounts of power. You're going to have large amounts of power at a given frequency when the numerator is not 0 and the denominator gets close to 0. That's when you get close to having a root. Remember that if you have a stationary causal armor model, the roots are outside the unit circle, but if a root approaches the unit circle, then the denominator becomes close to 0, and so the power becomes large. Now we want to see how this plays out in data analysis. How can this help us give insights to data? Well, let's come back to the Michigan winter data just to see what happens when we calculate the periodogram for this data and interpret it. Well, we have missing data for this. When we want to move to the frequency domain, we want to keep the proper timing of the data points, so we could replace the NA by the mean. There may be other things you could imagine doing. You could remove it. Whenever you have missing data, it's always unclear what is really a good thing to do. Ultimately, the data is just missing. So a good practical approach is to try everything that you think is reasonable and check that they all give the same answer. Or if they don't, then you found that there's some important sensitivity. So here is the unsmoothed periodogram, which is calculated here using the spectrum function in R. And as we discussed before, we're going to need to smooth the periodogram to get a good estimate of the spectral density, which will tell us which frequencies, if any, there's a pattern in Michigan winter temperatures. So, yes, let's move on to smoothing the periodogram. We're going to use the default periodogram smoother in R, and let's see how that goes. The default periodogram smoother is determined by these things called spans, and it produces this bar here. This is the confidence interval bar. And the way this works is, suppose there's some frequency you're particularly interested in, such as, say, this one. If we want a confidence interval, we would move the bar to here, and this is saying our confidence interval at this frequency at omega is approximately a third. That's a third of a cycle per year, which corresponds to one cycle per 3 years. And so there is a little bit of power here, but you see that there's not strong evidence in the data that any one frequency has that much more power than any other frequency. Now, why is this bar done like that? Well, the chi-squared property means that the confidence interval is the same width for each frequency on the log scale. So it has this nice property that you can just move this thing along each frequency and it just works fine. It's asymmetric because the chi-square distribution is asymmetric. And well, I guess this is a log chi-squared distribution, but that's still asymmetric. So we probably want to know a little bit about what that mysterious spans argument was for the default periodogram smoother in R. Well, what can we say? We specify a vector of spans, and each span, it turns out, is a window width for a rectangular moving average smoother, right? So you take the at each frequency omega, if this is a Fourier frequency and the span is 3, then if this is omega n, you have omega n plus 1 and omega n minus 1, and you have some periodogram values at these frequencies, and then you estimate the spectral density at frequency omega n by, in this case, just an average of those 3 values. Okay, and then what R does is, if you give it three spans, it first of all does an average with one of the spans, then it repeats this averaging process with another rectangular window. If you have three spans, it repeats it again. And so repeated smoothing with rectangular windows approximates a Gaussian kernel smoother. If you think about it, that's another way to think about the central limit theorem, that if you keep smoothing, you end up with something that looks like a normal distribution. This question of why this is the default has always seemed a little mysterious to me. I think it's chosen for historical reasons. So time series analysis is quite an old branch of statistics, and rectangular smoothing is easier to code efficiently. I should say calculate efficiently rather than code efficiency. People started taking the Fourier transform of time series data to look at frequency components before they even had computers. And then imagine doing a Fourier transform by hand, but people did. The main reason to do this nowadays is to conform to standard statistical practice. You need to use some smoother to smooth the periodogram. If you just use the smoother that everybody's used before, then somehow you don't have to justify it. If you did something else, you'd have to explain why you were doing something different. Okay, so if you really want to find out what R is doing when it calculates and smooths the periodogram, then you can get into the source code. Well, you can start off by reading the help. If you type $spectrum, it gives you a head start, but you quite soon find that the actual plotting is done by spec.pgram, and you look at the help on spec.pgram, and you see that R does a couple of other things that we haven't mentioned yet, that presumably it thinks it's worth doing, otherwise it wouldn't do them. One thing is removing a trend. In fact, it removes a linear trend fitted by least squares. And the other thing is doing something called tapering. Why does it make sense to remove a trend? Well, when the rationale for calculating the spectrum is all based around a stationary model for the time series. And once we remove a linear trend, then that stationary assumption is more reasonable. And at the very least, we want to remove an average, because otherwise the unusual behavior at frequency 0 is going to throw off our calculations. Okay, so what is a taper and why does R do it? The taper smooths the ends of the time series, and this turns out to be useful because it removes high frequency artifacts arriving from abrupt start and end to the time series. So essentially the math assumes the time series is 0 outside the measured interval. And so at the edges of the interval, it's going straight from 0 to whatever value it is. So you could have a really sharp edge in the time domain at the ends of the time series. A sharp edge in the time domain corresponds to nasty high frequency artifacts in the frequency domain, which we want to get rid of. And we do that by smoothing the end of the time series with a taper. Essentially, it throws away some of the data, but it turns out to be worth doing to avoid frequency domain artifacts. So again, if you dig around in the code, you can work out what R does, and that's probably a reasonable thing for you to do, at least as a starting point, and often as an ending point, unless you find you really want to think about it. The default taper in R smooths the first and last 0.1 fraction of the time points. And it does this using this kind of cosine taper, which normally we just use without questioning. But here is a plot of what it's doing. In the end, it looks almost like a triangular window tapering the end of the data towards 0. And here it is. So we have so far emphasized estimating the spectral density by essentially doing a smoother, a non-parametric method. You can also fit an ARP model with P selected by AIC. Sometimes that works well. I guess it works well when an ARP model is a good description of the data, which isn't always the case. We'll start learning by fitting time series models that quite often data have some sort of MA component as well as AR component, but it's convenient just to look at the class of ARP models, particularly if you're thinking P might get big. As soon as you get larger armor models, you get these numerical issues, and AIC becomes less reliable. Anyway, so you can do this. You can try all ARP models. You can see which AIC prefers. You can use this nice rational spectral density to calculate the spectrum evaluated at that best fitting model. And that is exactly what spectrum does if you use method equals AR. And for this Huron, for this Michigan winter data, it estimates a flat spectrum. It can't tell the difference between the data and white noise. One last comment I want to make on units of frequency and period for this chapter. We call omega frequency in cycles per unit time. We really mean cycles per unit observation, because observations don't always come in the natural units of the problem. And so when you're doing data analysis, when R is producing graphs or whatever, you may want to change the units so that you have the units that really correspond to your problem. So if the difference in time observations is delta years, then it's more natural to think of frequency in cycles per year rather than cycles per observation. So say if you have monthly data, delta is 1/12 of a year. And so you have to multiply the frequency by 12 to get to cycles per year. Also, sometimes with frequencies, it's a little less immediate to interpret the frequency. It's often more natural to interpret the period, and the period is 1 over the frequency. There you go. That's an introduction to the frequency domain, and we'll do some more with it in the next chapter.